So now we have a second talk of the day, and it's called Variational Inference, where I will briefly introduce the most popular way of what should we do if we are Bayesians and we do not have conjugate distributions. So the lecture will consist of two parts. In the first part, we'll derive so-called variational error bound, or known also as ELBO, evidence error bound. And in the second part, we'll consider one of the two popular variational inference techniques known as mean-field approximation. And tomorrow we'll consider the second variant known as stochastic variational inference. Okay, so let's recall what we've learned so far. So if we are Bayesians and we are trying to use Bayesian machine learning models, at training stage we are given training sample and we need to come up with a posterior distribution over the parameters to be estimated, as statisticians say, or the parameters to be learned, as we machine learners say. But actually, it's all the same. So we end up with a posterior distribution, and at the testing stage, we compute expectation of our predictions with respect to this posterior distribution. And posterior distribution itself contains all information we could extract about the parameters to be estimated, theta in this case, from our observable data from training set. Okay, so far so good, and the problem is that in many cases these two integrals can be intractable. So actually they are tractable only for very simple models where we can ensure, we can guarantee that we have a conjugate pair of distributions, and you've learned on practical sessions some examples of it, but unfortunately for the most interesting machine learning problems it is not so. I think we may even say that we may hope for establishing conjugate distributions only when we have a very limited training data sets. Because when we have a small data set, we tend to use simple ML machine learning models. But when we have large data sets, it's more preferable to use more complicated machine learning models such as deep neural networks. And in this case, we unfortunately can't guarantee conjugacy property. So then the question is, what should we do in the case when we don't have conjugacy, when we cannot get true posterior distribution in a closed form? So please pay attention that we can always get unnormalized version of a posterior distribution. Really, if we consider this Bayes theorem, we can see that numerator is pretty easy to compute. This is simply product of likelihood function and our prior distribution. So the only problem is that we cannot normalize this posterior distribution. So up to normalization constant, we can always have access to the true posterior distribution. And this is why the poor man's Bayes or MAP estimation is so efficient. Because when we're looking for the point of maximum of this function with respect to theta, this is equivalent of finding the maximum of just numerator. Because denominator doesn't depend on theta. It's just constant. Okay, so for the case when full Bayesian inference is intractable, or analytic Bayesian inference is intractable, there exist two main approximate techniques. One is known as variational inference, and it's based on approximating of intractable true posterior distribution with some tractable distribution, which is in some sense pretty close to the true posterior. And another approach is known as MCMC, or Markov chain Monte Carlo, or Monte Carlo Markov chain, I'm not sure. But probably Markov chain Monte Carlo. And in this approach, we try to generate sample, or set of samples from the true posterior distribution. So we cannot have access to the posterior distribution itself in analytic form, but we may generate samples from it, and using these samples, we may estimate, for example, expectations and, with respect to the true posterior distribution in an unbiased manner. So the pros and cons for both methods are shown here. So variational inference is known to be pretty fast and very computationally efficient, but the problem is that it's unbiased. Because instead of dealing with a true posterior distribution, we approximate it with a different distribution, so the results we obtain using these variational approximations will be biased. To the contrary, MCMC techniques is known to be unbiased, but the problem is that it's computationally very, very slow, especially when we talk about inference in huge dimensional spaces. Nevertheless, during the summer school, we will review both techniques. And very recently, about a year and a half ago, Another technique known as called semi-implicit variational inference has been also suggested, and we'll have an invited speaker who was one of the inventors of these techniques. Who'll give a talk on that, and this can be regarded as an attempt to take the best of the two worlds. So to keep the computational efficiency like in variational inference, but radically reducing the bias caused by this approximation, hence taking the advantage of the techniques based on Monte Carlo estimation. This is pretty new technique. It's still in the process of development, but I think it's important for you to know, to get familiar with one of the most promising approaches so far. But today we'll review the variational inference as the most popular tool for making approximate Bayesian inference. So if we'd like to approximate the true posterior with some variational approximation, first of all, we need to establish some kind of dissimilarity measure, some kind of distance between the distributions, which we will further minimize. And actually, there are several different ways, several different distances, several different pseudo-distances in the space of distributions, and one of the most popular is so-called KL divergence or Kullback-Leibler divergence. So this is a function of two arguments. Both arguments should be distributions. It's some kind of pseudo-distance in the sense that it's always non-negative and it equals 0 if and only if two distributions coincide almost everywhere. But it's not a distance. First of all, it's not symmetric. Second, the triangle inequality doesn't hold here. Nevertheless, we'll consider the problem of minimization of this KL divergence between our variational approximation and the true posterior distribution, and we'll try to minimize it with respect to the Q distribution, which lies in some restricted family of distributions Q large. Okay, so what is KL divergence? By definition, KL divergence is given by this equation. So this is the expectation with respect to the first argument of log ratio of two densities of first argument over the second argument. And as I told, it's always non-negative. It equals 0 if and only if two distributions coincide. Well, actually, almost everywhere. So up to the 0 measure. And it's not symmetric. And to get you some geometric intuition of what it is, let us consider the problem of minimizing KL divergence between Q and P and KL divergence between P and Q with respect to Q. So assume that this bimodal distribution is our true posterior distribution, and suppose that our restricted family of distributions Q large consists only of bell-shaped distributions, for example, only of Gaussians. So if we consider the minimization of this KL divergence between Q and P, where should we end? Or to what distribution will converge? Let's have a closer look at this expression. So what it shows, log of density ratio. Well, if two distributions coincide, the density ratio will be 1, log of 1 will be 0, everything is okay. But since we operate in the restricted family of distributions, we can never, we almost never may achieve 0 KL divergence, so there'll be still a gap between our variational approximation and the true posterior. And the question is when this gap will be large, when this gap will be small. So if this log density is large, then if the weight with which we perform this averaging is large, it's bad. So in some areas, this log density ratio can be large, but there should be such areas in theta space where Q of theta is small. Then even if this log density ratio is large, due to this multiplier which is small, KL divergence will still be small. And this means that in the areas where Q of theta is large, this log density should be close to 1. And this means that we have so-called mode-seeking behavior. So we place our Q distribution in one of the modes of a P distribution. So this is it. This is mode-seeking behavior. So we placed our bell-shaped curve around one of the modes in P distribution. So here log density is pretty small, and we multiply it by quite a large value of Q of theta. Here, the log density is large, but Q of theta is tiny. So it's negligibly small, and this is why this log density has almost no impact in the resulting value of KL divergence. Now let's consider the opposite situation, the opposite case. We minimize the KL divergence between P and Q with respect to the second argument. Then, when this log density should be small, in the areas where the first argument is large. The first argument is P. So in the areas where P is large, the density ratio should be rather small. And this can be done only by so-called mass covering. So we try to stretch our Q distribution among all the modes of P distribution. So in this case, where P is large, here and here, we still good density ratios. So they're about 1, maybe 2, or 1/2. And here, the log density is large. But here, the first argument, the P distribution, is tiny. And so these large log density ratios have negligibly small impact to the resulting KL divergence. So this is some geometric intuition of what KL divergence is and what is the difference between the inverse and between KL PQ and KL QP. And we will work with such kind of KL divergence, so which has mode-seeking behavior rather than mass covering. In the literature, there are also there are some methods which try to minimize the opposite KL divergences, but unfortunately, and as well as some other divergences, because there are many different divergences in the space of probabilistic distributions. But unfortunately, neither of them is scalable. Neither of them is applicable for the case when we have large data sets. And this is exactly the topic of our summer school. So we study only those Bayesian techniques which are scalable for the large data sets and for the large dimensions of parameters to be estimated, of thetas. And surprisingly, it appears that this technique is very, very scalable. So what we'll do further, we'll try to minimize this KL divergence between our variational approximation and the true posterior distribution with respect to the first argument. And here come two problems. Problem number one. In order to be able to compute this KL divergence, we need to have access to the true posterior distribution. But if we have access to the true posterior distribution, we no longer need any kinds of approximation. We already know the true posterior distribution. So it's quite problematic to minimize this KL divergence without having access to the second argument, because we just can't compute it. And second problem is, okay, assume that we somehow manage to compute this KL divergence. How will we minimize this KL divergence with respect to the first argument? This is the problem of function optimization. We try to optimize some criterion with respect to function. In our case, this is probability density function. So please raise the hands, those of you who do not know how to solve function optimization problems. Good. Actually, almost nobody knows how to solve it in general case. But fortunately for us, we'll come up with a couple of tricks that will allow us to efficiently minimize this KL divergence in a restricted family of distributions. So remember, keep in mind that this Q large is some restricted family of distributions. Because if there were all possible distributions among this family, then of course we would end up with the Q of theta equal to P of theta given X. But since we assume that true posterior is intractable for us, so we can't normalize it, we need to restrict the family of distributions to such family where all distributions are normalized, where we know normalization constants for all distributions within this family. Only then it becomes, this variational inference method becomes practical. Okay, and now let us have some mathematical magic. Now we'll derive some decomposition, which plays a very important role, at least during our summer school, but hopefully in practice as well. So I strongly recommend you to get full understanding of how it's derived and full understanding of its geometric sense. So assume that, we have this probabilistic model. So this is joint distribution over X and theta. We know this decomposition, so we know how to compute likelihood function, P of X given theta, and how to compute prior distribution, P of theta. And we're interested in approximating the true posterior, in approximating P of theta given X. which is by definition well, but by assumption is interactable. Okay, so let us start from log of P of x. So this is log of marginal distribution. And now we'll derive several identical transformations. Transformation number 1. Let us multiply log of P of x by 1. This is it. We take some arbitrary distribution Q of theta, and we take integral Q of theta d theta. And since log of P of x doesn't depend on theta, then this is simply identity. We can always move log of P of x outside of integral, and the integral will collapse to 1, right? Good. Next, let us write down our marginal distribution as follows, as a ratio of joint distribution over the conditional distribution. Is it clear why we can do that? Well, just let me show it here, just to ensure that everybody understands. So by definition, can you see it? Okay. Then just believe me. That remember the definition of conditional distribution. P of theta given x. This is the ratio of joint distribution over marginal distribution, right? So then the marginal distribution can be expressed as a ratio of joint distribution over conditional distribution. So this is it. Pay attention that this ratio doesn't depend on theta, because this is simply P of x, but both numerator and denominator depend on theta. And that's pretty nice. Next transformation. Let's multiply the expression inside of logarithm by 1. Q of theta over Q of theta. So this is still identity. And what we'll do next? How do you think? Yep. I guess it should be already available online. So any ideas of what we should do next? Right. So now we'll split this logarithm into 2 parts by taking joint over Q and by taking Q over 2 posterior distribution. And this is it. And we split the log, and hence we have split the integral into 2 parts. So what can we say about any of the parts here? Does it? Okay, I guess you know the right answer. Okay, let's have a closer look to the second term. So it's not difficult to see KL divergence here, right? This is expectation with some distribution over log of density ratio of 2 distributions. So this is simply KL divergence between Q of theta and 2 posterior P of theta given x. The question is, what about the first term? Is it KL divergence or not? Minus KL divergence. This is wrong answer. Who knows why? Yep, exactly. So from the first glance, at first glance, it looks pretty much the same like KL divergence. Well, like negative KL divergence. So we will put minus here, we'll reverse the arguments here, and we'll have an expectation with respect to Q log of Q over P. Pretty similar to KL divergence, but it's not. Because KL divergence is defined between 2 distributions over a similar domain. And here, this distribution is joint over x and theta, while Q is only distribution over theta. So it means that this is not KL divergence. For example, it can be negative. But it doesn't matter. What's important for us is that the second argument is KL divergence. So the first term is usually called L of Q, or variational lower bound, and the second term is KL divergence between variational approximation and the 2 posterior. So why the first term is called evidence lower bound? Remember that P of x is a denominator in our Bayes theorem, and denominator is known as evidence. And what we've done here, we use this decomposition, and the second term is always non-negative. This means that the first term is always a lower bound on the log of P of x. This is why it's evidence lower bound. Moreover, it's not just lower bound, it's so-called variational lower bound. And by variational, I mean that this lower bound holds true for arbitrary choice of Q of theta. when we choose it arbitrary distribution, it will still be a lower bound for the log of P of x, the lower bound for the log of evidence. Okay, now let us return to our problem of minimizing the KL divergence between our variational approximation, which is by definition some tractable distribution, and true posterior distribution, which is by assumption is intractable. Again, still we do not have access to the true posterior distribution. We can't compute this KL divergence, not saying about minimizing it. But fortunately, if we use our decomposition for the log evidence, what we see here, the left-hand part expression doesn't depend on Q, right? And the right-hand expression depends on Q. So we would like to minimize this KL divergence with respect to Q, but this is exactly equivalent to maximizing the variational lower bound. Because if we minimize this function with respect to Q, it means that this function is maximized with respect to Q. Because its summation, its sum doesn't depend on Q. Because they sum up to log of P of x that doesn't depend on Q. And this means that instead of directly minimizing KL divergence between Q of theta and our true posterior distribution, we may consider the problem of optimizing, of maximizing this variational lower bound with respect to Q of theta. And this is pretty nice because because in our variational lower bound, everything is computable inside of integral. We can compute Q of theta because it belongs to some tractable distribution family, and we can compute the joint P of x theta. Of course, the problem is that we also have integral here, and the integral is most likely to be intractable, but we'll now understand how we can still optimize it. But at least we do not need the true posterior distribution anymore, which we needed when we talked about the direct optimization of KL divergence. Here, we don't have it. This is nice. Now let us, before we start maximizing this variational lower bound, well, because this is our probabilistic model. So we always assume that when we work with probabilistic models, we always assume that we can compute the joint distribution. No. Here I consider the general case, but you may think of X as a training set and of theta as the weights of your deep neural network. So this joint distribution can always be decomposed. Well, this is exactly what I'm doing here. Can always be decomposed as a product of likelihood function times prior. Likelihood function is always given when we talk about machine learning problems. And prior distribution you may establish yourself. Okay, good. So now before we start maximizing this variational lower bound, let us try to understand what it really is. So let us try to get some intuition or some interpretation of what is ELBO. And to do this, first, I decompose this joint distribution as a product of our likelihood function and of our prior distribution. And then I split this logarithm into two, right? Into these two terms. So the first term is expectation with respect to our variational approximation of log likelihood of observed data, x in this case. And what is the second argument, the second term? Negative KL, because here the arguments are in the reverse order. So if we put minus here and if we switch the order here, we'll obtain exactly KL divergence between our variational approximation and between the prior distribution. So this is it. And now let us have a closer look at both terms here. Suppose that we now, for a moment, have access to all possible distributions in Q large family. So Q theta can be arbitrary distribution. And let us forget for a moment about the second term. And let us maximize just the first term with respect to all possible distributions Q of theta. how do you think where we'll converge? Why? Oh, this is the right answer. Because, look, this is log likelihood of observable data. You may think of it as a log likelihood of your training data, of your training set. And you would like to optimize the average log likelihood, where you take the average with respect to this distribution. And you would like to maximize it, to make it as high as possible. And of course, then the pretty obvious answer is that since we have all possible distributions here, we simply should use delta function at maximum likelihood point. So we put all probabilistic mass into the point where this function is maximal. So this means that the first term encourages us maximum likelihood estimation, right? Now let us forget about the first term and look just on the second term. And again, consider that we have access to all possible distributions Q of theta. If we maximize the second term, where will end up? P of theta, right. Because this is negative KL divergence, we'd like to maximize it. And we know that a negative KL divergence is always non-positive, and it may be equal to 0 if and only if two arguments are the same. This means that we simply put Q of theta equal to P of theta. And now we have both terms. So the first term encourages maximum likelihood estimation. The second term encourages convergence to prior. And the both term establish some kind of compromise between maximum likelihood expectation and between our prior distribution. And what will happen if we maximize the sum of the two with respect to all possible distributions Q of theta? Right, right. Because we know that maximization of the lower bound is equivalent to the minimization of KL divergence between Q of theta and the two P of theta given x. So this means that if we maximize this variational lower bound with respect to all possible distributions, we'll end up with a true posterior distribution. Of course, this is not possible since the true posterior is interactable by assumption. So we need to restrict the family of distributions among which we perform maximization. But nevertheless, so in some sense, you may consider this decomposition as a generalization of Bayes' theorem, because it does approximately the same thing. Establishes compromise between prior and likelihood, between prior and our observed data. That's why the first term is usually called data term, while the second term serves as a regularizer. So now let's turn to the second question. How to perform optimization in the space of distributions. So a kind of function optimization problem. And here we have two main approaches. Mean field approximation and parametric approximation. So today we'll review mean field approximation, where we restrict the family of possible distributions Q of theta by establishing these factorized constraints. So we split the space of our parameters theta into several groups, theta 1, theta m. Pay attention that they are not necessarily consisting of just scalar parameters, so they can be vector values. But what's important is that those groups do not intersect. So we split the whole space of parameters into these subgroups, and we establish such kind of constraint. We state that our Q distribution will be factorized as follows, can be represented as a product of m multipliers. Each multiplier is responsible for the distribution of the corresponding subset of parameters. So this is one way. So here we do not have any parametric constraints, and the only constraints we have are factorization constraints. And the alternative way is to establish parametric constraints. And this is, we simply state that we will search for the closest distribution to the true posterior in the space of some parametric family. So we parameterize it with the parameters lambda, and then we effectively convert the problem of functional optimization to the problem of parametric optimization. Because starting from now, we simply need to solve some parametric optimization problem, that is to find the optimal value of lambda. And this is what people can do more or less efficiently. But this will be the topic of tomorrow's lecture, and this is the key ingredient to the stochastic variational inference and to doubly stochastic variational inference, which we'll study tomorrow. And today we'll review the mean field approximation as some more simple technique. Okay, first of all, why this is a restriction? And the answer is pretty simple, because in the general case, we may use product rule, and we may always write down that Q of theta can always be represented as a product of conditional distributions. Qj of theta j conditioned on thetas with indices which are less than j. So this is the general decomposition, and here we use more simple decomposition. This means that this is restriction. So we assume that our joint distribution can be factorized as follows, and this means that those subgroups of thetas are assumed to be independent on each other. So this is definitely restriction. Sometimes it's crucial restriction, sometimes it's not. Okay, so what are we going to do next? So we have this variational bound, or our ELBO, and we try to maximize it with respect to Q of theta, which can be represented as follows, as a product Q1, Qm. And now we'll derive block coordinate update equations for each of the factors, for each of multipliers. So we'll consider our variational bound. We will fix all factors except one, except Qj, and we'll derive the equation for updating Qj. Then we'll fix that Qj, we'll switch to another factor and update it, and so on until convergence. Okay, so let us try to derive the corresponding mean field equation. So we start from variational bound, we split it into two parts. So this is the expectation of log of joint minus the expectation of log of Q. Now we substitute Q as a product of different QKs, and then the second term becomes just summation with respect to K from 1 to M, expectation with respect to QK of log of QK. Is it clear? Because all other terms will vanish. And what about the first term remains unchanged, and now we split this expectation, and we take explicitly the expectation with respect to J's multiplier. So my expectation with respect to Qj of what? Our expectation with respect to remaining Qis of log of joint. And here we take just the J's term here, and all other terms we treat as constant. Because remember, we now try to derive the update equations for Qj, assuming that all other factors are fixed. So this is block coordinate update equation. So then we can write down it as false. And now let's perform the following trick. Let's consider the expression inside of these square brackets. So this is some function of theta j. If we take exponent of this function, we'll obtain some non-negative function, a function of theta j. And now let us renormalize it. So let's divide it by normalization constant so that this guy becomes a probability density function, correct probabilistic distribution, which we'll denote as Rj of theta j. We can always do that because the exponent of this function is always non-negative, then we can renormalize it. And if we do that, we immediately can transform the first, well, these two terms as follows. So this term becomes log of Rj minus log of Zj, and log of Zj is just some constant. So we put it here. And the log of Rj will combine with a minus log of Qj. And it becomes the ratio, the log density ratio Rj over Qj. But then this expression is exactly negative KL divergence between Qj and Rj, up to some constant, which is additive. And now we try to maximize this expression with respect to Qj. So the answer is pretty simple. Since this is negative KL divergence, then the optimal Qj will be simply equal to Rj, right? And for Rj, we have an expression here. So this is exactly what we're going to do. So this is the iterative update equations. So this iteration, we consider each factor, and we update each factor as follows by equating Qj to Rj, which is exponent of expectation with respect to remaining factors of log of joint distribution, and divided by normalization constant. And this is the final algorithm of mean field approximation. So we initialize our factors, qj's, by somehow, and then at each iteration we update each of the factors by using this update equation and repeat this process of updates until convergence. We can monitor convergence either by examining the ELBO itself or just by looking at the factors qj. So when all the factors have stabilized, this means that we have reached convergence. This process is guaranteed to converge because at each iteration we increase our variational lower bound, and it's limited from above. So sooner or later we will converge, and in practice it appears that in the most of cases we converge pretty fast. The only problem here is this update equation, because in this update equation we first have this normalization constant, which is unclear how to compute it. And next we have this expectation with respect to remaining factors of log of joint distribution. Again, it's not clear whether this expectation can be computed in closed form or can't. And of course, we indirectly assume that we can compute it analytically. So the question is what are the conditions when we can compute those factors in a closed form? And this condition is known as a conditional conjugacy property. So it's pretty simple. Again, remember our model. So the joint distribution over theta, over x and theta. X is our observed data, theta are our unknown parameters. We split our theta into a group of non-intersecting variables, theta 1, theta m. And we'll say that this split has a conditional conjugacy property if the following holds true. So if our prior with respect to each subgroup, theta j, given all other variables are fixed, and our likelihood function as a function of theta j given all other thetas are fixed, form the conjugate pair of distributions. So if this is the way, then our posterior distribution over this subgroup theta j given x and given all other thetas fixed belongs to the same parametric family as our prior. So this is standard conjugacy property, and this conjugacy property should hold true for each subgroup of variables here. If we can guarantee this property, known as conditional conjugacy property, then we may guarantee, it's pretty easy to show, that these update equations can be done in closed form. So we will be able to compute this expectation, and we'll be able to renormalize each factor. So in practice, it's quite easy to check it. So we simply fix all subgroups except one, and we check whether there's a standard conjugacy property holds true for each of those subgroups of variables. And we will consider some examples during the practical session. So this is it, and in practice, instead of using this update equation, the people usually update log of each factor. So log of qj, then the equation becomes a bit simpler. So this is simply some additive constant and the expectation of log of joint distribution. So we have access to the joint distribution, hence we have access to the log of joint distribution, and due to the conditional conjugacy property, we may ensure that these expectations can be computed in a closed form. And so then up to additive constant, we have access to the log of qj, and this is generally enough for performing mean field approximation. And after we have converged, we simply state that we approximate our true posterior distribution with the q of theta, which has the following form. So this is the idea of mean field variational approximation, and this is a quite fruitful paradigm, which in many cases works pretty nice. And it's applicable in the cases when there is not full conjugacy property, so the full conjugacy doesn't hold, but if we split our parameters theta into subgroups, it may appear that for subgroups the conditional property holds true, and this means that we may perform mean field variational approximation. Okay, and just a couple of words about the alternative way of variational inference. This is parametric approximation, when we fix some parametric family, among which we'll try to find the closest Q distribution, the closest to the true posterior. Again, this is a restriction. because any parametric family always defines just a very, very narrow subset of all possible distributions. And if we take the too simple family, we may end up with a distribution which is very poor approximation for the true posterior. So it minimizes KL divergence, but because the parametric family was too narrow, we ended up with a distribution which is pretty far away from the true posterior. And if we use richer family of parametric distributions, it may appear that the variational inference becomes very inefficient and becomes too complicated. And we'll consider this tomorrow. What's interesting here, and probably this I will stress now, is that if we fix our Q distribution to belong to some parametric family, we effectively convert our function optimization problem to parametric optimization problem. So now this variational bound becomes just a function of lambda, and we should try finding the argmax of this expression with respect to lambda. And the problem is that this is still an integral here, and the integral in most cases is still intractable. So the question is whether we can optimize the function which we cannot compute in a single point. So if we fix lambda, we can't compute this expression because this is an intractable integral. However, although we cannot compute it, we are still able to optimize it, to maximize it with respect to theta. With respect to lambda. By the way, any ideas of how this can be possible? Right, yep. When I told once to my father, Daddy, you know, I can optimize the functions which I cannot compute in a single point, he told me, no, Sonny, you're doing pseudoscience. Please stop doing that. Nevertheless, this is really possible, and this is one of the paradoxes of big data, that we can optimize even those functions which we cannot compute in a single point. And well, just to summarize this lecture, so what options do we have right now? If we use Bayesian models, we may either perform full Bayesian inference and end up with a true posterior distribution. So if our distributions, if our likelihood and prior are conjugate distributions, this is always what we should do. If this is not the case and we're pretty silly or pretty lazy to study new math, we may simply use poor man's Bayes and end up with a MAP inference. This is simply finding the mode of this posterior distribution, and it corresponds to the approximation of the true posterior distribution with a delta function, well, with the delta function centered at some point, and if we minimize KL divergence between such delta approximations and the true posterior distributions, it is very easy to show that the optimal answer would be to put all probabilistic mass at the point of maximum. And this is exactly MAP inference or poor man's Bayes. It is very efficient, but it's quite inexact. So we're losing many, many advantages of Bayesian framework, such as ensembling, such as better uncertainty estimation than just using single algorithms. But if we're not so lazy and if we're a bit mathematically advanced, we can use some intermediate techniques, that is variational inference, either as mean-field variational inference, if we can find such subgroups of variables, such splitting of our theta space, that conditional conjugacy property holds true, or we can fix some parametric family and try to find the closest distribution to the true posterior within this parametric family. And this corresponds to parametric variational inference that we will study tomorrow. So this is it for the second lecture, and if you have any questions, I'll be happy to answer, right? Wait.
Looks like a coordinate descent. Are there any results about its convergence?
But why do you decide that it looks like conjugate descent?
Because coordinate descent works like when we fix all coordinates.
This is block coordinate descent. This is not conjugate descent.
No, not conjugate, but coordinate descent.
Coordinate descent. Yep.
Yeah, it looks like this. Are there any results about convergence of this algorithm? In this case, does it always work for some cases or?
It always converges. It always converges because if we use these update equations, we can prove that we always increase our variational bound. And our variational bound is limited from above. So it can be equal to plus infinity. And this means that we have monotonic convergence. So at each iteration, we keep increasing our variational bound until we reach local maximum. So this procedure is always convergent.
And it converges to the proper value, yes?
Well, that depends on what you call proper value. It converges to its local maximum, and as we know, all maximums of variational bound corresponds to minimums of KL divergence between our variational approximation and the true posterior. So we always converge to the minimum of KL divergence between our approximation and the true posterior. We can't achieve zero KL divergence because we have a restriction here, and in the case of mean field approximation, the restriction is factorization. So in the true posterior distribution is generally consists of interdependent. Well, in the true posterior distribution, the variables theta are not independent of each other. Here we imply these factorization constraints. Where here. So the true posterior may not look like that. So in the true posterior, these theta j's can be interdependent. This is why we cannot achieve zero KL divergence. But we converge to the closest, in terms of KL divergence, to the closest factorized distribution, the closest to the true posterior.
Okay,
so this is theoretically guaranteed. And this is direct consequence of the fact that we are using block coordinate optimization procedure.
Well, I have two questions. For the first question, could you please go back to the KL divergence slide?
Yep.
Yeah, so how can this work with multimodal posterior distributions?
What do you mean, how can this work?
So, as you show here, the green curve will at the end estimate like only one mode. So if the posterior distribution has multiple modes, then there will be like something like modal collapse to the other modes because we will be approximating only one mode.
Yep.
Is that right?
Yep.
So how can this work with multimodal distribution?
Well, it works just as shown in the picture. So if we use variational inference, we end up with a Q distribution, which is somehow approximates the true posterior distribution, but of course, it approximates just one mode.
One mode, right?
Yep, yep. That's true, but it's not that bad, actually. Because if we remember deep neural networks, we know that there's exponential number of modes which are symmetric and which are equivalent. So it's actually, there's no need of approximating all of them. It's enough to approximate just one of them, but to make good approximation around one mode. And this is exactly what we can do if, for example, we will use Gaussian distribution as our variational approximation.
But this will not result in mode collapse. Like, for example, I'm asking this question because I just know that GANs can have mode collapse, but variational autoencoders don't have mode collapse. So
it doesn't have mode collapse, but it has mode-seeking behavior. So we're trying to fit our variational approximation in the neighborhood of one mode. From this point of view, I think this can be called mode collapse as well, but that's a bit different mode collapse, and we'll discuss more the effects of mode collapse tomorrow when we talk about variational autoencoders.
My second question is very quick. So for the conditional conjugacy property, you said that we can check by just doing this. Yeah, if you can bring the slide. Yeah. Yeah. So this, if we do this check with a sample of theta, does that guarantee that this will apply for other samples of theta as well? Because we don't know the actual value of theta, right?
We do not know the actual value of theta, but here we do. That's not necessary. So all we have to do, so we have this probabilistic model, prior times likelihood. If we manage to find such kind of splitting of thetas into subgroups that for each subgroup, given all other subgroups are fixed, there is conjugacy property, then there's a conditional conjugacy. Holds true, and then we can make mean field approximation. We do not need to check it for some samples of theta. We should only have a close look at those two distributions. So we have these two distributions. We imaginarily fix all thetas except, say, theta 1. We check whether it holds true for theta 1. Then we check it for theta 2, and so on until theta n.
Oh, so we do it analytically, not... Okay.
Yep.
Okay, got it. Thank you.
So good? Yep.
Just a short question. Can you again explain a little bit more why this condition is the condition when I can apply mean field variational inference?
You mean why, if the conditional conjugacy holds true, why it follows that then we can make mean field approximation? Well, I'm afraid I would need another 20 minutes to explain that. So currently, please just believe me. Maybe this will, I guess that this will become more clear for you when you'll make several derivations. So when you'll study several examples of how mean field is applied. And this is what you're going to do today on the practical session. So the intuition becomes very clear when you derive a couple of times these update equations. But the formal proof is a bit complicated. So it's not so clear. That is why I decided not to provide you with a full proof of this property.
Thanks.
I understand that this algorithm converges, but I think that Q's are coupled to each other. So even though we are guaranteed to converge, wouldn't it affect the type of the solution? I mean, the distribution could be too compact that we could only capture the some mean of the data, I mean.
So if I understood the question, you express concerns that sometimes this could be very poor approximation for the true posterior.
Because of the coupling. They are coupled to each other.
Yes, there is always such a risk, and in general case there are no guarantees, and the only intuition is that the less subgroups are here, the tighter is our approximation to the true posterior. For example, if there were no groups here, if all thetas will be in one group, there would be full conjugacy property, and we would end up with a true posterior distribution without any kind of mean field approximations. If we split our theta space into two groups, we still have very good approximation for the true posterior. But if we split our theta in, say, 100 of groups, the approximation may be very poor. The more factors here, the worse is our approximation. Again, this is intuitively quite clear. Because the more factors we establish, the more constraints we have, and hence the further will be from the true posterior distribution.
Okay, thanks.
Sasha. Yep.
My question is about Kullback-Leibler divergence, and is there a case that if we use some kind of a mixture model, we can avoid single mode seeking?
Yes. So if you for example, use parametric approximation, and as a parametric approximation, you'll fix, for example, mixture of Gaussians, then you may converge to multimodal distribution. This is right. The only question is that, the only problem is that it's more difficult to perform variational inference when you use the mixtures of distributions. However, several recent papers introduce such formalism, such framework. This is known as hierarchical variational inference, where the Q distribution is assumed to have a quite complicated form. And again, we'll have a talk on semi-implicit variational inference, where Frank, I think, will cover this topic at least partly.
Thank you.
So to summarize, this is possible, but it requires quite advanced techniques, modern techniques for variational inference.
Thank you.
The reference is hierarchical variational inference, HVI. Okay, Sasha.
Thank you for your lecture. I have a question about ELBO and the mean field approximation. Could you please go through one more time about through the expectations and how we decompose them?
I'm not sure I understood
what the question is.
Yeah.
It's not clear how we decomposed the expectations in mean field approximation when we talked about ELBO.
So you mean the mean field update equations?
Yeah.
For the Qs? Yeah. So this is
those one. Yeah.
That one. Yeah. So I hope that up to now everything is clear, or not?
Yeah.
Yeah. Because here again, Q is a product of QKs, and we fix all QKs except QJ. So the corresponding terms are just constants for us. So we have omitted it here and put it in this constant. And the most tricky part is this transition. So what do? We split this expectation. Well, not split. We explicitly wrote down the expectation with respect to QJ and the expectation with remaining QIs, right? And then the expression inside of these square brackets is some function which is a function of QJ, because the remaining thetas have been integrated and the x is fixed because this is our data. So this is function of theta j. It can be positive, it can be negative, but if we take exponent, this function is guaranteed to be a positive function. Now let us renormalize it. So let us divide it by the integral with respect to theta j. So then it becomes normalization constant. And if we divide this expression by this constant, we end up with a correct probabilistic distribution. And we denote it as Rj. So this is a probability density function. We do it deliberately in order to obtain KL divergence here. So now let us return to the expression in the brackets. What is this? So this is the difference of two. The difference of two logarithms. Log of x vanishes, and we obtain exactly. No. Sorry. Okay. Let us express the expression in the square brackets in terms of Rj. So what is this? We first need to multiply it by Zj. Then we need to take the log, right? And then we end up exactly with this expression. So, but log of Rj times Zj, the log can be split into two parts. Log of Rj, which is here, plus log of Zj, which is some constant, which I put here. And then here we end up with a negative KL divergence. We did it deliberately in order to obtain KL divergence because we know how to minimize KL divergences. Because we know when 0 is achieved, when Qj equals to Rj.
And since variational inference is biased in relation to mean field theory, how can we reduce the bias? And what's the main source of that bias?
The main source of the bias is these factorization constraints. The less multipliers we have here, the less is the bias. The ideal case is when we don't have factorization constraints at all, but this corresponds to the full Bayesian inference. If we have some factorization constraints here, we introduce some bias. And if M is sufficiently large, this means that if the number of groups here is sufficiently large, then the bias will be stronger. The last question. because otherwise there'll be no lunch.
So in the conditional conjugacy example, usually we assume a functional form for the prior distribution and the likelihood. So now that we have to check for the conditional distributions of like the θ1 given the other thetas. So is it usual that that is what is assumed? Like, so this conditional distribution is assumed, and then whatever the joint distribution happens to be resulting, that's implicit. So when it's done in practice, is it that that's what is assumed and that?
Okay, good question. So look, when we establish this Bayesian model, we usually decompose it as a product of likelihood function times prior. The likelihood function is usually given for us. We cannot change it because it is defined by the problem we're trying to solve. And the prior distribution is there's some degree of freedom. So we may establish as we like. So the ideal way, the first way to do, we look at the likelihood function, and we ask ourselves whether it's possible to incorporate our prior knowledge, our prior uncertainty, in such term that this prior distribution would be conjugate to the likelihood function. If this is possible, we're done. Everything is okay, and the full Bayesian inference can be done in closed form. But unfortunately, in many cases, the likelihood function is too complicated. By complicated, I mean the space of parameters is too large. There are different parameters which define different things. And in this case, it's extremely hard to find the conjugate family from where we could take the prior distribution. And then we can ask ourselves, okay, I can't find the conjugate prior distribution. It may either doesn't exist, or it may either not exist, or it may exist, but it is so narrow, the parametric family, that it simply doesn't reflect our prior preferences. So we have our prior information cannot be fit into this narrow conjugate parametric family. And then we may extend, we may ask ourselves, okay, I can't find conjugate parametric family, but maybe I will be able to find conditional conjugate parametric families. So maybe I will be able to find such P of theta that if I fix all groups except one, then with respect to this one, there'll be conjugacy, and this will hold true for all groups of variables. So this is how it's usually done. And immediately after I establish such prior distribution, I know, okay, no conjugacy, but there's still conditional conjugacy, then I should run mean-field approximator, and I will end up with a more or less suitable approximation for the true posterior distribution. Okay, now guys, that's lunchtime, and we'll continue in an hour with the last lecture of the day.